take a slow breath. Let your mind settle into something vast. The story of the universe is not a myth, and it is not an abstract speculation. It is a reconstruction assembled from radiation that has traveled for billions of years, from the motion of distant galaxies, and from equations that describe how space-time bends under gravity. When we look outward through telescopes, we are also looking backward in time. Light from distant galaxies carries information from an earlier cosmic state. The farther we observe, the younger the universe appears. One of the most important discoveries of the 20th century was that galaxies are not stationary. Their light is shifted toward longer wavelengths, toward red, in a way that increases with distance. This is not simply a Doppler effect from objects moving through space. Instead, it reflects something deeper. The fabric of space itself is expanding. General relativity allows for dynamic universes. When Einstein first formulated his equations, he introduced a term to keep the universe static, because that seemed philosophically necessary. But the mathematics never truly supported a static cosmos. Once astronomical measurements confirmed large-scale recession, the expanding model became unavoidable. If space is expanding today, then earlier in cosmic history it must have been more compressed. Density and temperature would have been correspondingly higher. Extrapolating backward does not lead to an explosion in space, but to a state in which space itself was in a hot, dense configuration. This is what the Big Bang model describes. Not the creation of matter in emptiness, but the evolution of space-time from an early extreme condition. Our theoretical descriptions remain reliable back to a fraction of a second after the beginning. Earlier than that, quantum gravity effects likely dominate, and we do not yet possess a complete theory uniting quantum mechanics with general relativity. So we begin our narrative at the earliest moment where physics speaks clearly. At extremely high energies, the fundamental forces that appear distinct today may have behaved as a unified interaction. As expansion proceeded and temperatures fell, symmetry broke. Gravity separated first. Later, the strong nuclear force distinguished itself from the electroweak interaction. Still later, electromagnetism and the weak force became distinct. These transitions are not imaginative additions. They emerge from particle physics models tested at high energies. Very early in this evolution, the universe appears to have undergone a brief but extraordinary phase known as cosmic inflation. During inflation, expansion accelerated exponentially, smoothing curvature and stretching microscopic quantum fluctuations to astronomical scales. Those fluctuations, once subatomic, became the seeds of all later structure. The evidence for this lies in the cosmic microwave background, the faint afterglow of the early universe. Its tiny temperature variations encode a statistical pattern that aligns with predictions of inflationary models. When inflation ended, energy stored in the inflationary field converted into a hot plasma of particles. The universe was filled with quarks, gluons, electrons, neutrinos, and photons in thermal equilibrium. As cooling continued, quarks combined into protons and neutrons. Most matter and antimatter annihilated, but a small excess of matter remained, a slight imbalance that would determine everything that followed. Within the first few minutes, conditions allowed nuclear reactions to occur. Protons and neutrons fused into helium nuclei, along with trace amounts of deuterium and lithium. The proportions predicted by Big Bang nucleosynthesis match what we observe in ancient gas clouds, providing one of the strongest confirmations of this early epoch. For hundreds of thousands of years afterward, matter existed as an ionized plasma. Photons scattered repeatedly from free electrons, preventing light from traveling far. Only when the universe cooled sufficiently could electrons bind to nuclei, forming neutral atoms. With scattering drastically reduced, radiation decoupled from matter and began traversing space freely. We still detect that radiation today as the cosmic microwave background. Its temperature has fallen to just under 3 degrees above absolute zero due to expansion. Its fluctuations tell us not only about the early density variations, but also about the overall geometry and composition of the universe. At that moment, about 380,000 years after the beginning, the universe became transparent. It was not yet luminous with stars, but it was no longer opaque. What followed was a long interval during which gravity gradually amplified slight density differences. Dark matter, unaffected by radiation, had already begun clustering. Ordinary matter fell into those gravitational wells as the influence of radiation diminished. The process was slow. There were no sudden fireworks. Structure grew through cumulative attraction. Eventually, gas clouds within dark matter halos became dense enough for collapse to proceed beyond simple compression. Cooling mechanisms, limited but sufficient, allowed contraction to continue. In the densest cores, temperatures climbed high enough for nuclear fusion to ignite. The first stars were born. The ignition of the first stars did not simply illuminate the cosmos. It altered its chemistry, its thermodynamics, and its future trajectory. Until that moment, the universe had been composed almost entirely of hydrogen and helium, with only trace amounts of lithium. These elements were forged in the first minutes after the beginning, and for hundreds of millions of years, they defined all available matter. There were no heavier atoms to build complex molecules, no carbon to form organic chains, no oxygen to combine with hydrogen into water. The earliest stars changed that. Because the primordial gas lacked heavy elements, cooling during collapse was inefficient. This likely led to stars that were far more massive than most stars forming today. Stellar structure theory tells us that mass determines nearly everything about a star's life. Its luminosity, its internal pressure, the rate at which it consumes nuclear fuel, and ultimately, its fate. Massive stars burn intensely. Their cores reach extreme temperatures, enabling fusion beyond simple hydrogen burning. Helium fuses into carbon through the triple alpha process. Carbon can combine with helium to produce oxygen. In the most massive stars, successive fusion stages build heavier nuclei in layered shells, progressing toward iron. Iron represents a turning point. Fusion reactions up to iron release energy. Beyond iron, fusion consumes it. Once a massive star builds an iron core, it can no longer sustain outward pressure through nuclear burning. Gravity, which had been balanced for millions of years, suddenly gains the advantage. The core collapses catastrophically. In fractions of a second, densities approach those found in atomic nuclei. Electrons and protons combine into neutrons, producing a flood of neutrinos. The collapse halts abruptly due to neutron degeneracy pressure and nuclear forces, sending a shockwave outward. The star explodes as a supernova. In that violent moment, elements heavier than iron are synthesized through rapid neutron capture. Gold, uranium, and many rare elements owe their existence to such events. The debris from these explosions does not vanish. It expands into surrounding space, enriching the interstellar medium with heavier atoms. The next generation of stars forms from this chemically altered gas. With metals present, cooling becomes more efficient, fragmentation increases, and smaller, longer-lived stars emerge. Chemical evolution begins to layer complexity upon the universe. While stellar nucleosynthesis reshaped matter locally, gravity continued shaping structure on much larger scales. Dark matter halos merged hierarchically. Smaller systems coalesced into larger ones, gradually assembling proto-galaxies. gas flowed inward along filaments of the cosmic web, guided by gravitational potential wells established by dark matter. Angular momentum played a decisive role during these collapses. Slight asymmetries in mass distribution, amplified by tidal interactions with neighboring structures, imparted rotational motion. When gas cooled efficiently, it settled into rotating disks rather than collapsing entirely into spheroidal forms. Over time, recognizable galactic structures emerged. Spiral galaxies developed flattened disks and central bulges. Elliptical galaxies formed in environments where repeated mergers disrupted ordered rotation. Irregular systems reflected turbulent assembly histories. In the centers of many of these forming galaxies, black holes began to grow. Some likely originated from the remnants of massive early stars. Others may have formed through the direct collapse of dense gas clouds under special conditions. Once present, these black holes accreted matter from their surroundings. Gas spiraling inward formed accretion disks, where gravitational energy converted into radiation. Under high accretion rates, the energy output could rival that of the entire host galaxy. These luminous objects are known as quasars. Observations of quasars at extreme distances reveal that supermassive black holes existed less than 1 billion years after the beginning. Their rapid growth remains an area of active theoretical investigation, but their existence underscores the tight relationship between galaxy formation and black hole evolution. Empirical correlations between black hole mass and properties of galactic bulges suggest feedback mechanisms. Energy released by accreting black holes influences star formation within their host galaxies. Thus, gravitational collapse not only builds structure, but regulates it. Across billions of years, galaxies assembled into larger groupings. Clusters of galaxies formed, bound by enormous dark matter halos. Between galaxies within clusters lies hot, diffuse gas heated to tens of millions of degrees. This intracluster medium emits X-rays, revealing the mass distribution within clusters. Gravitational lensing, the bending of background light by massive foreground structures, provides additional evidence of dark matter's dominance. The visible matter within galaxies accounts for only a small fraction of the total mass required to produce observed gravitational effects. On the largest scales, galaxy surveys reveal a vast filamentary network, the cosmic web. Dense clusters lie at the intersections of filaments, while immense voids separate them. Despite this intricate structure, when averaged over sufficiently large volumes, the universe appears homogeneous and isotropic. The same underlying equations that governed early expansion continue to apply. As cosmic time progressed, star formation rates peaked roughly 3 to 4 billion years after the beginning. This epoch, sometimes called cosmic noon, marked the height of stellar production. Thereafter, star formation gradually declined as gas reservoirs were depleted or heated by feedback processes. In one unremarkable spiral galaxy, about 9 billion years after the beginning, a molecular cloud within a rotating disk began to collapse. The gas in that region had already been enriched by previous generations of stars. Dust grains formed from heavy elements facilitated cooling and molecular chemistry. Within that cloud, gravitational collapse produced a protostar at the center of a rotating disk. Conservation of angular momentum prevented all material from falling directly inward. Instead, the disk served as the birthplace of planets. Over millions of years, dust grains collided and stuck together, forming planetesimals. Gravitational interactions allowed these bodies to accrete into larger objects. In the inner region of the disk, where temperatures were higher, rocky planets assembled from silicates and metals. Further outward, gas giants formed with thick hydrogen-helium envelopes. Approximately 4.5 billion years ago, the Sun entered stable hydrogen fusion. The Earth formed soon after, enduring a violent early history marked by impacts and volcanic activity. The raw materials for chemistry were present: carbon, nitrogen, oxygen, phosphorus, sulfur, all products of stellar nucleosynthesis. Under suitable conditions, increasingly complex molecules formed. At some point, chemical systems capable of replication emerged. Life began. The pathway from simple chemistry to biological systems remains under investigation, but its ingredients were cosmically prepared. The arc from primordial plasma to planetary biospheres did not require new physical laws beyond those already active in the early universe. The same gravitational attraction that shaped dark matter halos enabled molecular clouds to collapse. The same nuclear processes that powered early stars produced the elements essential to life. Now consider the broader cosmic trajectory. For much of its history, the expansion of the universe slowed under the influence of matter's gravity. However, observations of distant supernova in the late 20th century revealed that expansion began accelerating roughly 5 billion years ago. This acceleration is attributed to dark energy, represented in the standard cosmological model by the cosmological constant. Unlike matter, whose density decreases as space expands, the energy density associated with the cosmological constant remains constant per unit volume. As the universe grows larger, the relative contribution of dark energy increases. Eventually, it dominates the dynamics of expansion. Today, dark energy accounts for roughly 2/3 of the total energy density of the universe. If its properties remain unchanged, expansion will continue accelerating indefinitely. Galaxies beyond our local gravitationally bound group will eventually recede beyond the observable horizon. The night sky, in the distant future, will grow darker as external galaxies fade from view. Star formation will continue declining. Gas will be consumed or expelled. Stellar remnants, white dwarfs, neutron stars, black holes, will persist long after active star formation ceases. Over extraordinarily long timescales, even black holes are predicted to evaporate via quantum processes described by Hawking radiation. The evaporation timescale for supermassive black holes vastly exceeds the current age of the universe. But in principle, no structure is permanent. Entropy continues increasing. The universe moves gradually toward thermodynamic equilibrium. This long-term fate is not dramatic in the way human narratives often imagine endings. It is gradual. Expansion stretches distances. Energy spreads thinly. Structures fade. Yet within this immense timeline lies a remarkable interval. An era during which stars shine steadily, heavy elements circulate, and planetary systems form. You exist within that interval. The early universe set initial conditions that allowed complexity to arise. Slight density fluctuations seeded structure. The laws of gravity amplified them. Nuclear reactions forged new elements. Chemical processes built molecules. Biological evolution produced conscious observers. The universe did not abruptly transform from simplicity into awareness. It unfolded through continuous physical processes. When we examine cosmic history carefully, we do not see disconnected stages. We see a single evolving system governed by a consistent framework of physical law. Space-time expands according to general relativity. Particles interact through quantum fields. Thermodynamics directs energy flow. Gravity shapes structure. Fusion powers stars. The initial state was hot and dense. The current state is vast and structured. The future state will likely be colder and more dilute. Between those states lies the entire story of galaxies, planets, and life. You are composed of matter that has traveled this path. The hydrogen in your body dates back to the first minutes. The heavier elements within you were forged in stellar interiors and explosive deaths long before the sun formed. To reflect on the birth of the universe is not to contemplate something separate from yourself. It is to trace the history of the matter that now forms your body and the physical processes that permit your thoughts. The universe began in a state of extraordinary energy density. It expanded, cooled, and differentiated. Through gravity and quantum fluctuations, structure emerged. Through nuclear fusion, complexity increased. Through chemical evolution, life became possible. The same expansion that began billions of years ago continues now. Even as you rest, galaxies recede. Stars radiate. Dark matter shapes motion. Dark energy stretches space-time. The birth of the universe was not a single moment of spectacle. It was the beginning of an ongoing evolution. And that evolution continues, quietly, lawfully, persistently. Take a slow breath. Imagine the cosmic microwave background still filling space with faint radiation. Imagine distant galaxies drifting further apart. Imagine stars quietly fusing hydrogen into helium, all of it part of one continuous story. From an early hot, dense state to a structured cosmos capable of awareness. The universe did not emerge complete. It became, and it is still becoming. Rest now. The cosmos is vast, but its laws are consistent. Its history is long, but it is coherent. And within that history, you are a brief but remarkable configuration of cosmic matter, aware of the journey that brought it here. Sleep gently. The expansion continues.